Okay, so now let's go over plane waves and well, how do plane waves relate to what we just discussed with in terms of Maxwell's equations? To be completely honest with you, we can analyze plane waves without understanding Maxwell's equations, and we will. I just feel that since Maxwell's equations are the fundamental equations that govern all electricity and magnetism, we should at least have the ability to discuss what they mean. You can now relax in the comfort of knowing that we're never going to use Maxwell's equations to actually calculate anything in this course. I just wanted you to be exposed to those, so you've suffered through that now. So let's move on to plane waves, which is really what the purpose of this video lecture series is. And to discuss plane waves, what we want to discuss is some sort of time-variant electromagnetic field. And so we've got some sort of radiating point source, and we know that this radiating point source, in addition to producing a time-varying electric field due to the voltage and current that are flowing through this point source, it's also going to produce a time-varying magnetic field. And so both exist simultaneously, and they cross-link together in this time-varying electric field, which is created by the source, which is usually a voltage source, like the modulated voltage on an antenna. It's going to create a time-varying magnetic field, which is created due to Ampere's law. And since this induced magnetic field is also time varying, it's going to introduce a second electric field. And so what is happening here is that as the E field, as it's collapsing, it converts its energy to an increasing B field. The B field will reach its peak when the E field reaches a zero. The H field will then begin to collapse. It'll transfer its energy back into the E field. And what's happening is as one of the field components collapse, it passes its energy into the next, and energy is being passed back and forth between the E and the H fields as they radiate away from the point source. So each of these lines represents an E and a B field collapsing and expanding as they move away and decouple from this radiative point source. And all of this is occurring at the speed of light, and this is how electromagnetic energy is transferred. It radiates away from the point source in coupled, collapsing and expanding electric and magnetic fields. Under most conditions, these waves are going to radiate away from the point equally in all directions, meaning that they radiate away spherically. I'm showing circles, but you also have to imagine that this radiation is occurring into and out of the computer screen. So in this direction, and then into and out of. So you can easily imagine a point enveloped by a sphere, and that sphere growing larger and larger and larger in terms of its radius. And this is a pretty good picture of what an ideal EM wavefront actually looks like. And this is typically what is called a spherical electromagnetic wavefront. However, if we go far enough away from this radiating point source, the radius of curvature gets smaller or I guess larger and larger and larger. Here's a very tight circle. The radius of curvature here is getting smaller. If we go far enough away, the radius of curvature has gotten so large that the wave appears as a straight line, and we call this a plane wave. It means if I were to put some sort of receiver over here, all the electromagnetic energy contained in the wavefront strikes this receiver at the same time. And you can imagine if we put a little receiver over here, the wavefront here strikes before here and here. This is a much harder situation to analyze. If we just assume that the EM wave impinges on the surface all at the same time, we call that a uniform plane wave. And so we've got in this picture, we've got a plane wave moving from right to left, meaning that we've got E and H fields that are radiating up and down and into and out of the page. So wave direction is in that. We've got an E or a B field moving that direction and an E or a B field moving that direction, right? They have to be orthogonal to the direction of the plane wave movement. So in E&M, we have a special term for this. This is called a transverse wave, meaning that the direction of energy transfer is perpendicular to the direction of actual oscillations or the direction of propagation. And we're going to analyze plane waves in the rest of this section because they're easier to understand than these spherical wave fronts before. What we'll do is to show how Maxwell's equations, or simplified version of Maxwell's equations, govern wave motion in the case of these sinusoidal waves. And we're going to look at the characteristics of the media that this wave is traveling in, and we're going to see how the characteristics of that media influence the propagation. And then finally, not in this video, but in the next, we're going to look at what happens when waves change from one media into a second media. And that's what we're really going to study in plane wave. So in our analysis of transmission lines, we developed an equation for voltage and for current as functions of time and distance along the transmission line. And these equations, these time harmonic voltage and current equations, are special cases of what we call the general wave equation, which is the equation that fully describes electromagnetic waves traveling in any medium. And what we're going to do is we're going to assume that this wave, this plane wave that we're talking about, is x-polarized, meaning that the E field is traveling in the x direction. And this is just giving us a reference. We can write the general solution for a plane wave, which, remember, consists of two parts, an E field and an H field. And we would say that the E field, as a function of z and t, is equal to E bar plus e to the minus, e to the minus alpha z cosine of omega t minus beta z plus e bar minus e to the plus alpha z cosine of omega t plus beta z. And we said that this is going to be x polarized A, just meaning that it propagates in the x direction. And similarly, there's a magnetic field strength, h of z comma t, and that is, you can probably guess, h bar plus e to the minus alpha z cosine of omega t minus beta z plus h bar minus e to the plus alpha z, I'll write it down here, cosine of omega t plus beta z a hat y, right? And obviously I skipped a lot of math to get here, but we did this math already for a voltage and current waveform, and so I'm just going to write the results now. I think we've done enough calculus for a little bit. And so the general solution to the plane wave equation is that the plane wave consists of two fields, an E field that is x-polarized and consists of a forward traveling electric field component and a wave component, and a reverse traveling electric wave component. And there's also simultaneously exists an H field. It's at a right angle to the E field. It's perpendicular to the E field. And it also consists of a traveling wave that has both a forward and a reverse component. So therefore, we say that the plane wave is characterized by an E field in one direction, an H field that is perpendicular to the E field, and the direction of propagation of the plane wave is perpendicular to both of these, in this case in the Z direction. Typically, by convention, we just define the E field as pointing in the A hat X direction, the H field is pointing in the A hat Y direction, and the direction of travel is therefore in the plus Z direction. The right-hand rule for plane waves can be used to determine if the wave is traveling in the plus or the minus Z direction. And what you do with the right-hand rule for plane waves is you take your right hand and you take your thumb and you point it in the direction of propagation of the E field. You take your index finger and you point it in the direction of propagation of the H field, and then you hold your middle finger perpendicular to those two, and that gives you the direction of wave propagation. So those are the general wave equations. And I'm actually going to break this video into two parts, so I'm going to stop here and just start a new video.